Thank you. So I will introduce myself now. So I guess I can warn you that my probably strongest point as a speaker is complete inability to finish on time. So this time I get fancy, and I'm going to probably summarize my talk in about 3 slides first, so that I get the content out, and then it's going to be followed by a bunch of demos trying to prove the points I made, and we can skip and jump over the ones as time goes. So hopefully I will be on time this time. So the other day Arden let me in on a secret that not everyone bends and minces libraries for a living. So I should probably tell a little bit about what I mean when I say security here, and why should people care at all, and where can they see it? So that's an interesting thing that if the security is any good, you shouldn't really see it. Good security should be invisible, and it should really only present itself, and when it does, then it should be only when there's something wrong. So TSA certainly isn't a good security. The other thing is that even if you didn't see it, you probably use it every day. It's spreading quickly everywhere for quite a while now. And with the world being increasingly interconnected, it's used throughout pretty much. So you're probably using it even if you don't know it. The specific bits that I want to talk about here are usually hiding on the bottom of these various technology stacks that are used to build applications. So if you imagine one of those typical layered diagrams of systems, at the top level you have some applications like a web browser or an email client. At the lower level there would be some application protocols like HTTP, SMTP, and whatnot, and they will have their variations with the S at the end, and the S is where the security lies. And it's implemented in the lower levels using specific security protocols like TLS and SSH, X-file certificates and things like that you may have heard about. And underneath all that are the actual things that make them work, which are the actual cryptographic algorithms, like AES, RC4, SHA, might be the acronyms you've heard or seen somewhere. So what I'm talking about is really the bottom 2 layers, the algorithms at the bottom, and then the protocols about that, directly about that, the specific security ones. So in this talk, I'd like to summarize what we actually have new in our product, in our new release that's coming out soon. We've provided security library for quite a while now, probably a decade by now. But what we had so far was complete Smalltalk only implementation of everything, from the algorithms to the higher level protocols all the way up. And it's great, it's very flexible, it works everywhere, you just start your image, it's there and it works. So it has its good sides, but there are also some very good reasons why you may want something different, not the Smalltalk implemented version, but some external one. Among those reasons are things like security is a very touchy subject, and it's very often very tightly controlled by norms, standards, requirements. Your organization may be required to use only implementations certified in a certain way in this part of the world, and so the Smalltalk implementation may be great, or as much as it wants to, but unless given certification is not available, it's no good for you. So definitely you may need to use something that's basically forced on you as a user, because your industry or your company or whoever requires you to use only that. Another reason might be a technical reason, like you may want to take advantage of some hardware implementations or hardware appliances to perform certain cryptographic functions. So you may have smart cards with RSA key embedded in them. The key never leaves the smart card for security reasons, and the card itself performs the RSA computations. So you may need to hook up into something like that. Another reason that that motivated us as well was that as much as we tried the pure Smalltalk implementation, sometimes just doesn't meet the goals in terms of performance. It's cryptographic algorithms are primarily bit twiddling at the very low level, and that's not where our Smalltalk implementation can really outperform something that's pretty much tied to silicon. Nowadays, even your phone probably has an actual circuit in it that does AES encryption, not even assembler code. So we can't really match that, and sometimes you need that sort of performance. So one of the big changes in this release is actually opening up to these other implementations. And out of the box, we will be shipping with 2 backends for Microsoft Windows. We hook up to the new API they call CNG, cryptography new generation or something like that, or often labeled bcrypt. This API is available in Windows Vista and later. At this point, I'm not aware that they would be that Microsoft would provide some sort of service pack that would make it work on XP. I don't know how that's going to be resolved, but that may be an issue. On any other platform, we expect to use a fairly well-known library called OpenSSL, which in itself provides services like SSL protocol, but we use only a small part of it, the heart of it, called libcrypto, which is the library that provides the cryptographic algorithms. So this library ships pretty much on any recent Linux. It ships with Mac OS X. It is available and can be compiled on pretty much any Unix platform. So that's why we picked this one as our target on the other platforms. But as I said, we have tried to open up to other implementations that the users might want to hook up into. So we support 2 already. We should be able to hook up any number of other ones into the same APIs, and our high-level frameworks will be able to take advantage of those. With this big sort of, it's sort of like replacing an engine in a car, so there's a lot of changes that come out of that. Some of the changes were, again, changes that we wanted to make because we think the APIs can be improved, the scalability, performance, so some of these changes are motivated also by that. So we are changing the core, the cryptographic algorithms quite significantly. We are switching to a new streaming API for the hash functions and ciphers. And also, since these libraries normally ship with the public key cryptography components as well, we provide new public key APIs to give you access to that as well. And also with the switch, you get access to some new algorithms that you didn't provide before, like, for example, SHA 512 bits and stuff like that. This is, however, dependent on the actual backend that you're going to be using. So bcrypt has a different set of algorithms compared to libcrypto, for example, or whatever else you might be using. So that's the changes, summary of the changes at the lowest level there in terms of the algorithms. At the higher level, we have the same set of high-level frameworks as we had before, namely these 4 mentioned on the slide. But as I said, the engine underneath is changing, and some of those changes have some implications at the higher level as well. So the PKCS5 framework, which is a framework for encrypting and signing data using passwords. It's a standard-based technique. That didn't change at all. There shouldn't be any impact at the API level and how to use it. The PKCS8 is a standard for secure storage and transfer of private keys. That one has minor changes due to the new public key APIs. I have all these things, examples of all these things in the following slides. We'll see how many of those we'll be able to cover. The X509 framework is the public key certificates that you may have probably seen one way or another. There are things that you can see in web browsers. Again, I'll show a little demo of that. Again, not many changes there, just the impact of the public key APIs, and we extended the algorithm coverage there, so now you can actually use certificates that are RSA signed with SHA-256 or 512. You can do that now with our X509 framework. And the biggest and largest change at this layer is our basically completely rewritten SSL TLS framework. So previously we had SSL implementation. Now, one thing I should clarify, SSL and TLS are actually the same protocol. It's just that originally it was designed by Netscape, and then when IETF took it over, they renamed it to TLS. So this is a fantastic opportunity to get completely confused. But basically, SSL3.0 is the old version, and then after that comes TLS 1.0 and 1.1, and most recently 1.2. So it's all basically just 4 versions of the same protocol. So before we had only SSL 3.0, now with this change, with the complete overhaul, we have support for all 4 versions of this protocol. With this change, we also support new modern algorithms. In the old implementation, basically you had the choice of triple DES or RC4, and that was it. Now we support the new AES algorithm, which is the federal standard algorithm that we really need. And again, new versions of SHA and other things. Also, the other goal of our overhaul was to basically, again, open up the implementation to enable some things that basically weren't feasible before. For one, our performance wasn't good enough with the pure Smalltalk implementations to play any significant role on the server side. For client side, it was mostly fine for pretty much any use, but on the server side, where the server needs to handle, 20, 50, 100 concurrent SSL sessions, that's a completely different ballgame, and the performance is critical there. Even with a pure SSL stack, C or assembler stack, on a really large sites, we have a lot of hardware acceleration involved in the backend to actually make it happen. So, but with a plain Smalltalk implementation, that's pretty much a non-starter. So we also wanted to open up with this rewrite. We actually have performance that you could deploy decent server site with it. But there's also other things that you need to deal with, things like load balancing, SSL sessions, and things like that. So for that, we want to be able to hook up to external third-party SSL load balancing and caching mechanisms and things like that. So we have a flexible session management building. We also want to be able to plug into external or third-party certificate and key management facilities. We have the one implemented by our X509 framework, but it's always a bit of a pain for people to configure. This should open up open up to us the possibilities, for example, to hook up into a certificate stores that come with your operating system. And so that's the brief summary. It's all downhill from now on, so this is a good opportunity for any questions if you have. Okay. So now I basically want to go through the various topics I covered here and show some examples. The first set of slides is about the lower level, about the algorithms. I always have a slide how it was done in the old framework and how it is done now. I'll probably skip a few of these because it's going to take too much time, but this first one is, I think, interesting. So let's talk about the hash algorithms at first. Here's a simple example where we take a string, hello, we turn it into a binary, and you would compute an SHA hash like this. You take the algorithm and you say hash and give it a string. So hash of a hello looks something like this. Now, in reality, you find out you rarely hash hellos. More often, you need to hash fairly large files. So it doesn't look nearly as nice at that point. So let's say you want to hash the image file that runs this presentation. We'll need a binary to basically so that we can read the file efficiently in chunks. We'll need the instance of the algorithm. We'll do MD5 this time. We will, actually I should probably just get this running and then I'll explain the bits. Oops. So file is the stream, stick IM, binary, make a read stream, and then the loop is pretty straightforward. We read the file until we are at the end, and we will first read buffer size worth of data into the buffer, and then update the hash function from the buffer in the second line here, update with buffer. And we keep repeating until the file is closed. And I should have started it before I started talking. Last time I timed it took a little bit over a minute. Should be close to that now.
What are you running on, Martin?
Oh, this is yeah, that's a good point. This is basically a netbook, so this is much faster on a normal machine. So this is a poor Atom 350 or something, 4 or 5 years old now. The image file is somewhere in the vicinity of 70 megabytes. So this is the pure Smalltalk implementation. We profiled and optimized the hell out of it. I don't think you can make it more, another 20 or 30% faster. You might be able to shave off a little bit, but that's about it.
Can I ask a question while we're waiting?
Yep.
I know that what you said about the need, sometimes you're required by external parties to use certified binaries or something for particular algorithms. But whenever it's just yourself wanting to be secure and not required to use something, have you read the end-to-end argument from David Ungar? Are you familiar with that?
I'm not sure I read the paper, but I heard about the argument, yeah.
Basically saying that unless you do it yourself, you can't know for sure if it really got done, if it really was secure, like something like digital security. It goes out over the pipe, it comes out of the program to another layer of the program. And so maybe that would be a case where using the Smalltalk at the Smalltalk layer to encrypt something within the application. So for example, if the hard drive got stolen, then even on the hard drive it's encrypted.
Yep.
I guess that's not really a question.
Yeah, I was just looking for the question.
Yeah. Well, and then the other question was about the key exchange protocol. Something that's very complicated if you don't exchange a key in person, or it can be, at least from what I've studied. Is that something that you have had to do a lot of thought and work into?
We support, the public key algorithms are about that. It's there are algorithms that allow to. The problem there is authentication, right? The problem is you can get a key, you can get a public key of someone, but you don't know is it really his public key, right? And that's what experiment certificates are about. And there are different approaches. The certificates are one of them that help with that. Are they perfect? No. But it's a complex topic. I don't think I can get much into that, too deep into that. Anyway, it looks like I finished. 1 minute, 28 seconds. So thanks for helping to occupy the time there. So 1 minute, 28 seconds here. And then you would get the digest by asking the hash for the digest. So that's the digest of this image file. Now if we go to the next slide, and surprise, let's do it here. So one change that you'll see right away here is that the API is quite different. And the idea is that if you look at the previous slide, the API with the hash is sort of like stream, using a stream. It's just not a stream API at all. So what we were experimenting for a while in the context of a framework called Extremes is basically why not just turn it into a stream. So Extremes is sort of an alternative take on how streaming could be done. And it builds with this notion where you can stack streams on top of each other and streaming between transformations as the data flows through. So there's the cryptography bits could be done as just one layer in this sort of stack. So that's exactly what we're doing here. We first make a file stream, and Extremes we make a stream by, say, reading to something. So here we say reading to a file name. Then we will set up a hashing layer on top of that. We tell you which algorithm to use. So I'll use this one here. And now in the Extremes API, you can copy stream. So you can copy streams. You can just use stream as an argument to a write or read operation. So here we will take that readable stack of readable stream with hashing in the top, and we'll write it into a stream which is nil writing, which just means this is a sort of an efficient big bucket. You can write into a nil, anything gets written gets just thrown away. And so if we time this guy, 1 second, so it's quite a difference, I think. And so then you close the stream and you can ask it for the digest, and there's the digest of the file. Now the reason why we like this approach to play streams is that normally you don't just hash the file, you normally do also other things with it. So you can compute another hash with it at the same time as you're reading it. Hashing MD5, not file, but that needs to be on top of SHA. And let's say at the same time we will want to, the top level is going to be MD5 during, and with each byte we will make a little frequency table. So no, I don't want a snapshot. Why would I want a snapshot now? Either a new 256 with all 0, so that's our frequency table. MD5, and so here, if you want to know how many of which byte were there, we say f at b+1 put f at b+1.
Why don't you use a
bag
for that?
I have, it's even slower. Yeah, I can use a bag, but
But that's okay.
yeah. So here we go. This one's a little slower. Not even that much slower. Was it that fast because I did something wrong? Yes, it was. I need to write the top on SHA. All right. So go on. And that's an interesting one. F.
Yeah.
It's a binary.
Oh, I thought that said T, sorry.
Yeah, it's kind of, I don't know why.
T.
Is it a T? All right. No, it says F. Let me just type it in. I really need to debug this.
It's probably more than, you have more than 256 occurrences of a character.
No, this is a binary, so this is bytes, 0 to 255.
Yeah. So as soon as you have a as soon as the counter is more than 256, its error occurs. You must have an integer array or anything like that.
That's
You know,
not
Don't make it a binary array, make it an array instead of a byte array.
Can be an array. Oh, right. You're right, that's it. All right, yeah, array. Of course, yeah, the numbers are going to be a lot bigger than 250, 255. So this should be more than 10, 15 seconds. Yep, there we go. So with, here we have, with one read, we have the frequency table, so we see that 0 is there about 8 million times. 255 is only 300,000 times, so there's a serious imbalance in this image file. But anyway, that's the frequency table. At the same time, let's close the stack. We can see that we've computed the SHA and D5 as well. Yep. There we go. So that's just to show that why we think this streaming layered approach is an improvement over what we had before. So, I get 50 more minutes. That's serious. So next is was a similar demo about the ciphers. I had here a demo how to take the image file and we can encrypt it here. This is a padding at the end of there. We will compress it and hash it at the same time. So we end up with a 20 megabyte file here. Neat little demo, I thought. Again, it's from the ciphers area. The public key algorithms, they changed a little bit as well. Previously, you would instantiate a class of the algorithm, and you would first generate the keys using a generator, and then you set up the algorithm, set up some other parameters, and you can sign the message and verify the signature or encrypt the message, things like that. The new API is different. There is no algorithm class. There is one generic private key and public key class, and here's how we would generate a key. The signing API is slightly different here to give the various parameters. Right there, you can configure an algorithm or a key, but conceptually, it's not that different. I'll skip the PKCSA as well. It's mostly about the private keys, and let's get to the, I guess, last demo there. For that, we will need a certificate because I want to demonstrate SSL server, and so we will need a certificate. So let's do this demo. So a public key certificate is exactly what it says. It's a certificate that has a public key embedded inside. So let's generate an RSA key of 2048 bits. To get a public key, you just ask the private key for the corresponding public key. And now to get a certificate, we need to make a name, which is the name that's embedded in the certificate. So here we'll have stick212. Name is actually quite a complex structure in X509, so this is a very simple one. And now to set up a certificate, you need to give it a serial number. We'll make a self-signed certificate, which means the issuer and subject of the certificate is the same name. The validity is going to be from today for 100 days. This is the public key that we are going to stick in. We need to assign some sort of usage for the key. So if you want to use it as an RSA key, as an SSL certificate, then 4 key exchange is a reasonable setting for the certificate. And then finally, this is the main change in the X509 layer. We have slightly different key, public key API again. So before you would hand in a pre-configured algorithm, now you hand in the key and specify the other parameters as part of the API. So now we have a public key certificate here. You might have seen this sort of output. This is a standard OpenSSL output of a certificate. So you see the issuers here, subject, validity, the embedded key, the signature at the bottom. Now, one thing that's different as well is that now the public and private keys are not Smalltalk objects, not only Smalltalk objects, they are actually fairly complex structure living on the C heap. So all you get from Smalltalk is a handle to something. And so this needs to be managed. So when you're done with the keys, you have to release them. So we'll release this key. You don't need it anymore. The other change is also that now when you ask the certificate for public key, you won't get a usable key, the key that you can immediately use as before. You would get this X509 version of the key, which basically shows the members, and you have to convert it to a usable public key after that with this get key method. So let's move on to the TLS example. So one way, or the easiest way to use TLS is actually buried under a bunch of different frameworks. So as you can see here, the easiest way to use it is to just evaluate, get an HTTPS URL. So let's open the login tool so that we can see a little bit what's going on here. And let's do the get to Google. And here we have the response, 200 OK. So let's see what actually was going on. So just a little bit of an overview to see how much is actually going on in the back end when we do something like that. So here we are starting off by sending a TLS hello. We are offering the latest version of the protocol 3.3. Let's get packaged up as a record. We receive a record back which contains a TLS server. Hello, Google apparently doesn't support TLS 1.2. Winning. And Google picked RSA, key exchange with RC4, 128-bit, and SHAs for signatures. Send us its certificate, and finished its hello. And then we send the client key exchange back using that certificate. Finished handshakes here. Now the encryption is on, and this is finally our get going out. And we get a bunch of data from Google. For some reason, Google sends its stuff in tiniest chunks, 26 bytes. The whole response is a lot more, but I don't know why. And here is the response from Google. So that's actually from what went on. The next little bit in the example shows roughly how this gets set up on the Smalltalk side. It's very similar to what you used to do before with the old SSL framework. Again, there's a context and the connection, and you ask for a stream, and then you read from it or write into it. It's fairly straightforward in that sense. Let's look at the server example instead. It's a little bit more obscure because I can't really do it in the socket level like in this slide, because most web browsers, I want to show it with the web browser, and most web browsers immediately open up at least 2, 3, 4 connections, so the code will be a lot complicated. There's no way I can fit it on the slide. So what I'm going to use here is a sort of a simple web server goodie that you can find on VisualWorks with distribution. It's called OpenTalk www. And I can set it up. It's basically based on OpenTalk, as the name suggests. If you did anything, this is an OpenTalk configuration expression, and there's an HTTPS transport for it. And there's a version of the adapter that can play the role of a simple web server. So to set up the TLS side of things, you need this thing called the certificate store, which is our basically front end for the certificate and key management facilities. The default goes back to our X509 implementation. Now on the server, you also need a certificate and a key, because the server always needs to authenticate to the client. So you need a server key. So we use the certificate that we used in the example earlier. Now we need the context. You need to give the context the certificates. And now we set up the server. Now the server is fairly simple. It just gets an HTTP request, and it has a set of executors that each get a chance to look at the URL, and if they like it, they'll do something, and if not, they reject it. It gets passed to the next executor. So here I'll have two. One is able to handle files, basically serve pictures from this file subdirectory here. The other one is a simple web echo. So here we set up the server. This part is just to show you how many connections are being opened. So it basically prints the transcript every time a new connection is opened. And we'll start the server. So let's take a quick look. Here. And I think this is the echo. So first thing, this is actually to be expected. Basically, Chrome opened a bunch of connections and closed them because it didn't like the certificate. You can see it doesn't trust the certificate because it doesn't know anything about stick 2012. So we'll proceed anyway. And here we get the echo. This is from one of the executors that simply echoes the request back and tells us a little bit about the connection. So this is how we connected. RSA is 256. It's TLS version 3.1, which is TLS 1.0, just to make things more confusing. That's what it means. So that's the echo. Together the files. We just downloaded a picture from the web server. Now I wanted to talk about the boats, but we don't have time for that. So another picture. These are really cool boats, by the way. I don't know if you noticed, but it doesn't have a main sail, it has a wing.
I can see.
Yes?
5 minutes.
Yeah, 5, okay. Yeah. So, anyway, I'm not going to waste another 5 minutes of time talking about boats. Quickly try to summarize. Yes? So, again, there's a lot of potentially external resources involved here. So, the cleanup again is important here. You need to release the context when you're done with it, because there could be external resources. In this case, there's a resource which is a secure random number generator that needs to be released. Similarly, the certificates need to be released. They are not released as part of the context because those two things get a completely different life cycle. And we want to reuse the same certificate store with a bunch of different contexts and vice versa. So it's a bit more maintenance. Arguably, the old implementation didn't require to do it, although we should have, because if it's not about releasing resources, there should be actually cleanup going on. For example, if there are pieces of private key or other secrets, they should be securely wiped out, cleaned out before they are released. So just relying on them being garbage collected is not actually good security practice anyway. So it's not exactly making the situation worse, it's just making it more visible, I guess. This is just a brief summary of the extension points that are now available. There's certificates which completely contain any key management and public key operations and certificate processing. The TLS implementation basically doesn't know anything about certificates. It sees them as binaries. And so you can completely encapsulate that and plug it into whatever other certificate solution you want to use. Similarly, the session management, there's a session cache, which can implement various strategies how to manage the caches. Session management is very important for performance in terms of SSL, especially for the server. The handshake is extremely expensive. And so when a browser sets up 3, 4, 5 connections right off the bat, every time if it does a full handshake, it's extremely expensive, especially on the server. It doesn't matter on the client, but if your server is supposed to handle many of those, it's much better if the clients actually resume sessions. That's what they call it in the TLS terms, meaning there's a much cheaper way to establish the same session over the following connections. Only the first one pays the big price, and the following connections can be established much cheaper. So that's what the TLS session management is about. Extremely important for a scalable website. The bulk encryption and key exchange algorithm setup is also encapsulated in these things called TLS cipher suite that you can configure. And again, you can plug in your own implementations, and similarly with compressions. The following few slides are another bit that is a goodie that is also available in these things. Pretty neat thing. We have basically a full implementation of SSH protocol as well. I can, if you're interested, just let me know. I'd be happy to show you bits of that. What's left to do at this point? We would like to put in a way. Well, basically, originally when we started this work, our plan was to basically drop up-to-date version of libcrypto, or in some of these cases you may want to. It might be more convenient for you to fall back on the Smalltalk solution. So that's something we would like to do. There's more things to do. We could do on the TLS side. There's many options now that open up for us that we would like to pursue as well, and hope to in the following releases. So just to summarize quickly, there's more implementation options for you that you can take advantage of. We support more algorithms. Everything, there is a big emphasis on making things easily extendable. It's significantly faster in a lot of scenarios. There might be scenarios where you won't see performance improvement, but we see, in some scenarios, we see improvements in terms of 20, 30, 40 times faster than before. Up-to-date SSL TLS support, we are, again, fully caught up. We support whatever is available, so we are in much better shape there as well. And we are finally basically capable of handling server-side load in terms of TLS, which is significant for us as well. So I'm out of time, but if we are allowed a few questions, I don't know.